As you can see, we have talked about a lot of things on post and zero. First video post on zero, second video post and zero, third video post and zero, everything post and zero. Macam. So anyway, let's talk about something not very post and zeros. So we talk about second order step response or second order impulse responses. So as you remember, step responses are saying that you apply a step input into a transfer function. Alright, so in order to get, so imagine, not imagine, but rather you remember the transfer function is equals to the output over the input. So if the input itself is step, then you have a step response, right? So therefore, in this case, for step response, our transfer function, as you know, second order, is this long chunk of stuff over here. So in order to get step response, you have to multiply with a 1 over s, right? So when you multiply 1 over s into this equation, you'll get something like, hold on a while. I don't know what the fuck. Yeah, you'll get this equation, okay? Because okay, when you multiply step response, okay, this portion over here, except the s, okay, except the s is the step hold on a while. So this thing is actually the transfer function, and this 1 over s is the step input. Okay, so when you multiply inside, in order to because you want to inverse Laplace ma, so you have to use final value theorem, final fraction, partial fraction, partial fraction, or what do we call cover up rule, whatever the case, eventually you'll get this one. So this one, as you can see, is you eventually get this deal over here. Okay, this is the value, and maybe I think I'm wrong. So when you do this, if you inverse Laplace, you'll get this formula, 1 minus e. Okay, and you may found this equation very familiar. It's actually in your modeling formula sheet. Okay, it's the same thing. So similarly, in your control, you also get this equation. Okay, it's the same thing. But slightly different is that you have a k, you have a multiply with k over here. Okay, but everything is about the same. If all these things are all given, and then this is talking about the step response. Okay, step response, and then now we talk about impulse response. Okay, so for impulse response, let me scroll up because actually I didn't see it. So for impulse response, as you remember, is as I also have mentioned earlier, it's the amount is when you input a step input, impulse input inside. Okay, so in this case, impulse input is 1. So therefore, the transfer function itself is just this thing over here. Okay, this transfer function is this thing over here. Okay, or otherwise, this one. Okay, without the k. It's a little different from the formula sheet, so you have to really take note. This one is actually the output is equals to the amount is equals to the transfer function times k times the input. Okay, so it's one chunk together, like a buy one get one free type of thing. So so when you multiply a step response, okay, impulse response, impulse response is 1, right? So you didn't change the formula, and in order to make it in terms of t, okay, you introduce an equation, okay, for that is in here. Okay, omega is equals to omega n 1 minus damping factor square. And take note that this is different from just now when we talked about the equation for finding the s. S is 1 minus damping square, right? Sorry. Okay, hold on. Okay, at the very first part, right, when you do the transfer function, the denominator, if you were to solve for the quadratic, you eventually get this equation, right? So this is in terms of damping square minus 1, which is different from your 1 minus damping square. So you have to be very careful, and this actually given in the formula sheet, so you can just straight away use this. But I don't think they'll ask you to derive anything, unless but it's pretty easy if you were to know how to derive. So let me derive this for you. Okay, you give me a while. So you have to derive this transfer function, okay, is given into this thing. Okay, I mean really into this thing actually. So how are you gonna do? Okay, the first step is to do we're gonna do is to use completing the square, if you remember. So hold on a while. So if you don't know how to use for completing the square, it's okay because I also don't know. But I think in the test they will actually show you this one at first, then they say derive the following transfer function into this. So okay, you know this one, and then you just expand this one into this. Okay, so this portion is equivalent to this one. Okay, so I hope you can actually go and memorize how to use completing the square. It's pretty useful, I think. So you do completing square for this portion over here. You just divide everything by just divide. You know that this is but anyway I also forgot. So you just know that this is the expansion of this. Okay. So therefore, if you were to rewrite this form, the denominator only, we are talking about the denominator only, because everything we are concerned is about the denominator. So this portion is actually this, while this portion is this one. So how do you get this one? Okay, so you give me a while. So in order to do that, you have to use this formula. Okay, so this formula, what is this formula? You just square this one. Okay, so hold on a while again. So eventually my objective here is actually to prove that this one can be equals to this one square. Okay, so therefore if you were to factorize this one, you factorize the natural frequency square out, you will get 1. Actually this is minus, sorry, my fault. Okay, this should be minus. Hold on a while again. Okay, why is it minus is because this portion is equals to this portion, right? However, it is however this thing does not exist in the equation itself. We only have this one, this term, and this term only, right? You can see we have this term the same, this term the same, and this term is the same. So this one is equivalent to 0. This is why I minus. Because in order to make this thing square, because as I say earlier, this portion here is equals to this. So that's why I minus this dude over here. That's why this thing is minus. And then we add in this one. Okay, I hope I didn't confuse you, because last minute then I realized something wrong. Okay, but nonetheless, this is minus, so therefore, this is 1 minus, okay, 1 minus damping square. If you were to, because this is minus already, so if you were to factorize out omega n square, okay, they are the same term. You factorize out, this is 1 minus the damping square. Okay, so what you can see is that this portion here is, what do we have? If you were to expand this thing, it will be m square 1 minus square, which is the same thing over here, right? So this is equals to omega square. And what is this actually is the damping frequency. Okay, so natural frequency, if you forget, okay, natural frequency is when the system is keep oscillating, it's free from any friction, any damping effect. But for damping friction is natural frequency including the damping forces, maybe resistance in the air, or maybe the damper itself. So this is the W itself, okay, is the damping frequency. Okay, when you square it, it's something else lah. So with this in mind, I hope that you understand why this equation here is, omega square is what we have derived earlier. So this portion is what we have derived earlier. Okay, so yeah, and then the top one is simply you introduce, because this will eventually cancel out, so this one will be equals to this one. So I hope I didn't make things complicated. So this is just so maybe I do a summary again. Hold on. So in order to turn this equation into this equation, the denominator part, okay, I do completing the square. Okay, I got this one, which is equivalent to this one. Okay, then because this does not exist, okay, so we minus this one plus this one. Okay, and then eventually you will get this, and this is actually omega square. So for this we have set it up for the Wn square s plus this portion over here. Okay, but now because this is not in terms of some Laplace formula that we can actually convert, so this is why we use, since it's known there is an omega, okay, and it takes on some form of the Laplace, so we have multiply with omega and the portion over here. So as you can see, this is the some constant, okay, c, while this is actually e minus omega nt. Okay, omega nt is just omega natural frequency is just this portion over here, and then sine omega t, which is omega is this two. Okay, so it takes on the formula for the Laplace formula. If you remember, it takes on 1 over s plus a multiplied by this one. Okay, I mean not multiplied by other than, actually it's not given here, so you have to be careful when you're dealing with it. So I don't know, I believe you will understand what I mean. Okay, so for the while again, I thought I have done a good job, but rather than confusing you, but yeah. So in the next video I'll just talk about overshoot, because I have no time, 12 minutes already, so I'll see you there.